Welcome back. This is now the 17th lecture of the condensed matter course. When we left off last time, we were talking about band structure, and we were talking about electrons in conduction bands and holes in valence bands. And what we're going to do today is we're going to start by thinking about how electrons in conduction bands and holes in valence bands move around. So let's start by drawing the bottom of a conduction band. So we have some E and some K, and there's going to be some quadratic minimum of a conduction band. Let's call this point here K min, where the bottom occurs, and this point here we'll call it E naught, the energy of the bottom of the conduction band. Very generally, maybe I'll write it over here. Very generally, we can write for an electron near the bottom of the band that E is approximately E naught plus just the Taylor expansion, d squared E dk squared times K minus K min squared, maybe other terms which we'll ignore. And given this, we will define an effective mass, an electron effective mass, effective mass m star sub electron via 1 over m star electron equals 1 over h bar squared d squared E dk squared, such that the energy is E naught plus the usual h bar squared k minus k min squared over 2 m electron star. Now this looks very much like a free electron, except the momentum, the wave vector should be measured with respect to wherever the minimum in the momentum is. It's the usual free electron parabola. Now, given this, we can also calculate, actually given any form of the energy of the electron in this band, we can write a group velocity, V group, very generally is d omega dk. That's a general expression for a group velocity, since we can replace omega by 1 over h bar times an energy, dE dk. This is the general relationship for the group velocity of an electron in a band. In our case, it will be, using this dispersion up here, it will be h bar k minus k min over m star of the electron. So it means that if you have this picture over here, if you move the electron to the right of the minimum, then the electron is moving to the right. If you move the electron to the left of the minimum, then the electron is moving to the left. This is true independent of where in the Broughton zone the minimum occurs. So really the issue is where you're positioned with respect to the minimum if you want to figure out which direction your group velocity is. Now there are a couple of caveats. Maybe I'll write them here. Caveats. One, generally effective masses, right, this masses may be anisotropic. Masses can be anisotropic, meaning that the energy it may be parabolic in all directions, but depending on which crystal direction you choose, the curvature may be different. This is sort of natural if you have something like a tetragonal crystal where the axes are different lengths in the different directions. You might expect that the curvature of the energy in the different, displacing k in the different directions might be different, and indeed it often is. So one has to worry about the fact that depending on which way you're going, your effective mass may seem different. We're going to ignore this generally. So ignore this complication, but more generally, you should be aware that it does occur. The second complication that you should be aware that occurs is you can have situations, if you plot E versus K, you can have a situation where there are two minima that occur at exactly the same energy, this, E. So that the minimum of the conduction band can occur at two places in the Broughton zone, K1 and K2. These are known as valleys for obvious reason. And this may look like it's something that's very unusual to have happen, that you have just such a coincidence that the minima, that the same energy occurs at the minimum in two places in the Broughton zone. But in fact, it's actually quite common to have this due to symmetries of the crystal. So generally, this will happen if the crystal is particularly symmetric. You'll have 2 minimum in the conduction band at 2 different points in the boron zone, or even 4 different points, or even 6 different points of the boron zone. So you have to keep track of whether the electron is in this minimum or this minimum. But the general rule applies that if you displace yourself from the minimum to the right, you're moving to the right. If you displace yourself from to the minimum to the left of the minimum, then you're moving to the left. Okay? Now the final point, generally, we're going to ignore this complication also. Ignore this as well. Just be aware that it sometimes occurs. The final complication is perhaps a much more important complication. If you have a band structure, here's a boron zone. If you have a band structure like the tight binding band structures we drew before that looks like this, generally, the effective mass is given by the second derivative of the energy with respect to k. So that would mean that m star of the electron here is greater than 0, but up here, m star of the electron would be less than 0, which seems rather odd to have a negative mass for a particle. But we'll see in a moment that actually makes quite a bit of sense, and really we should think of the mass of the electron as being negative. The general definition that the mass of the electron, 1 over h bar squared d squared e dk squared, will always hold, and that's what we should always think of as the effective mass. Okay? So far so good? This was the easy part. The hard part is when we start thinking about holes at the top of a valence band. So the reason it gets hard is because minus signs will come back and bite you one way or the other. So it's really hard to keep track of the minus signs. And to make matters worse, some books put the minus signs in different places. So this is one of these situations where as long as you know what you're doing, you can move the minus sign around. If you have the even number of minus signs at the end of the day, you got the right answer. But what I'm going to tell you is what I think is the most natural way to think of where you put the minus signs. And I think most books agree with me on this, but not all. So be warned about that. So this is the situation with holes at the top of valence bands. Top of bands. So that means up here, where we found this odd result that the mass of the electron is negative. When we're thinking about the top of a band, like over there where we found this odd result, we're usually thinking, when we're at the top of the band, about a nearly filled band, a nearly filled valence band. So we'll draw again E versus K, and we'll imagine that we have the top of some band, which is mostly filled, and we'll think about, okay, we'll put this at K max, and okay, and we will call this E naught also up here. We imagine if we put an electron up at the top of this band somewhere, its energy is going to be, okay, so for the case of holes, top of band, the energy of an electron, E electron. It's really good to keep in your head track of whether you're talking about an electron energy or a hole energy, because you'll see that they're going to get confused in a second. So the electron energy, if you put an electron near the top of the band, that will be some E0 plus 1/2 d squared E dk squared times K minus K max squared, exactly the same way as it was before. But now this quantity here is negative, so this is less than 0. And this is why we should think of the mass of the electron here as being a negative quantity, because the energy actually goes down as you go away from the maximum. So here, what we're going to do to make our life a little bit simpler is to define a mass of a hole. Define mass of hole to be h bar squared over m whole star is minus d squared E for the electron, dk squared. So this thing here is greater than 0 at top of band. And you will notice from comparing this definition to the above definition that the m star of the hole is actually equal to minus m star of the electron. Okay? So up here, where the mass of the electron appears to be negative, we've defined the mass of the hole to be minus of that. Now, why is it that this makes sense to do? Why is it we should define the mass of a hole to be negative the mass of the electron, and why should it be the mass of the hole be positive at the top of the valence band? So let's think about this for a second. So here we have the same top of the valence band. We imagine the whole valence band is filled, except for one hole, which we're putting at the top of the band here. Okay? So the energy of the hole, E hole, must be some constant, E naught twiddle. And then we want to find out how does the energy of this hole change as we displace it from the top of the band. So let's imagine this point here, just so we don't have to carry around these k maxes and k mins anymore. Let's decide this point here is k equals 0. As we displace k from, this is just for simplicity, it doesn't have to be at k equals 0, but let's imagine it is. Let's ask what happens to the energy as you displace the hole from the top of the band. So we're going to move the hole from here to here. Well, when you do that, the energy actually has gone up from displacing the hole from the top of the band. Why is that? We'll write it as h bar squared 2 m star hole times, I guess, k squared here, if we're displacing it from k equals 0. The reason that the energy has gone up when we displace the hole from the top of the band is because the electrons are trying to go to the lowest energy possible. The holes try to bubble up to the highest energy possible. It's like an air pocket or a bubble, or like pushing a balloon underwater. If you take this balloon here and you push it underwater, that costs you energy. It costs you positive energy to take this hole and push it underneath the electrons, because the electrons want to go to the lowest energy possible. Is that clear? That's the intuition of why it is that you should think of the mass of the hole as being positive, because when you displace it from the top of the band, it costs you positive energy to move away from the top of the band. So far, so good? Okay, good. All right. So that's the easy sign to keep track of, but signs get more complicated. Let's ask about the momentum of a hole. What is the momentum of a hole? Momentum of a hole. And a good way to think about this is to realize that a filled band has no momentum, has no crystal momentum. No crystal momentum. Carrying no current, it's inert, has no crystal momentum at all. So if we want to know what the momentum is of a hole in the top of the band, let's imagine here's our band. We fill the entire band like this, except for one state which is missing out of a k state like this. We imagine taking this hole, this missing particle from the band, if we add it to a band that's empty except for that one electron placed in, then this plus this equals a filled band, equals filled band, filled band. So momentum, so total momentum equals 0. Total h bar k equals 0. Okay? So the sum of these two put together, the filled band with the absence of the hole plus the empty band with this one electron, sorry, the filled band with the absence of this electron plus the empty band with the presence of this electron, when you put them together, their total momentum is going to be 0. So what we have then is h bar k for the hole over here plus h bar k for the electron should, which is over here, should give us a total of 0. So far, so good? So that means that h bar k for a hole must be minus h bar k for the missing electron. Okay? So that's a good way to keep track of what the momentum of a hole should be. There's one of these confusing minus signs. Now let's think about, given this, what the velocity is of a hole at the top of the band. These things are all actually going to end up being important, because you need to know which way the electrons or the holes are moving. Keeping track of it for an electron at the bottom of the band, everything seems very natural, but a hole at the top of the band, everything starts getting confused, so it's important to keep track of these correctly. So let's think about velocity of hole at top of band, So again, we start with the energy for the electron at the top of the band. So that's E naught minus h bar squared k squared, k electron squared over 2 m star whole. Okay, now why did I draw it this way? So m star whole is greater than 0. The energy for the electron decreases as you increase the momentum of the electron away from k equals 0. The band is curving down, so the energy for the electron is decreasing. The group velocity then, which is always 1 over h bar d, so this is the group velocity for the electron, d e electron dk electron, is then minus h bar k electron over m star whole. Or, since m star whole is minus m star of the electron, we can write this as h bar k e over m star electron, but m star electron is less than 0. So what this means is if I had an empty band like this, and I had an electron here near the top of the band, the velocity of this electron is actually going this way. B group is going this way, right? Because you can think of that as the electron mass is negative because of the negative curvature, so the group velocity is actually in the opposite direction as the wave vector. Okay? I know it's confusing, but you know, if you just keep track of the signs carefully, everything comes out correct. Let's compare that to the energy, to the situation if we think about it in terms of holes. So the energy of a hole near the top of the band is some constant plus h bar squared k whole squared over 2 m star whole. So the energy of the hole increases as you increase its momentum away from the top of the band. So the group velocity, V group whole, equals 1 over h bar dE whole dk whole equals h bar k whole over m star whole. And k whole, we just decided, is the same thing as minus k for the electron. So this is the same thing as minus k h bar k electron over m star whole, which is in fact the same thing we just calculated up here. So the point here is that if we have a filled band like this and one empty state here, the group velocity of that is going in this direction as well. This is an extremely important principle that will come back many times, or at least several times, that the velocity of a state, the velocity of an orbital, is independent of whether that orbital is filled, whether the orbital is filled. So you can think of it as you have a bunch of orbitals in your system, and the orbitals have some velocity. You can put an electron in that orbital, and the electron will move with that velocity. If you remove the electron from that orbital, the orbital is still moving with the same velocity. It's just there's no electron in it. Okay? So this is a kind of an important principle, which it actually makes a very good amount of sense. I mean, when we think about we think about hydrogen atom or something, we think about these orbitals being there whether or not there's an electron in the orbital. And the orbitals can be moving with some velocity, and they're still there and moving independent of whether we put the electron in or we didn't put the electron in. Okay? All right. So let's now actually try to take what we've learned and calculate some dynamics of electrons and holes. Dynamics of electrons and holes. And the simplest way to handle dynamics is what we started the term with, which is to think about Drude theory. So we're back to Drude theory after many weeks. And so let's recall the Drude equation that we derived. Some P dot equals F, just Newton's equations with a drag term, P over tau. And we can write that out for electrons. For electrons, we will have mass of the electron, I'm going to put a star here, times v dot. So the only thing different from what we did at the beginning of the term is I'm now putting a star next to the mass. So it's the effective mass, the curvature at the bottom of the band that matters, not the bare electron mass, which is not an important quantity in a semiconductor or an insulator. It will have the force, the usual Lorentz force, which is always with you. That was another joke. All right, never mind. V over tau for the electron, the scattering time for the electron. So this should look fairly familiar. This is the Drude transport equation that we had before. There's some acceleration, and mass times acceleration. There's some force. There's a charge of minus e on the electron. There's a Lorentz force, and there's a drag force here. This equation holds true whether we're talking about an electron near the bottom of the band or an electron near the top of the band. However, near the top of the band, the sign of the mass gets to be negative. And that seems a little bit weird, but if we think about it near top of band, we can consider Drude equation for holes. So we would have an m star hole times the velocity of the hole, same Drude equation, but the charge on the hole is now plus e. Write this again, equals plus e. The charge on the hole is plus e. Then we have e plus v cross b, Lorentz force, and then minus m star hole, velocity of the hole, over some scattering time for the hole as well. So we have a Drude equation for the holes at the top of the band as well. Now, remember that we have two things here. We have two equations, one for the electrons, one for the holes. And the difference in the two equations is that the sign of the charge is different for the electrons and the holes. But also, m star hole was defined to be minus m star of the electron. So in fact, these two equations are exactly the same. If it's just this equation has been multiplied by an overall minus 1, m star hole is minus m star of the electron. And so it's actually just repeating exactly the same Drude equation. So this is actually quite important. It's exactly the same statement that I just wrote over here. The dynamics of the state are exactly the same whether you're talking about an electron moving in the state or a hole moving in the state, the absence of an electron. The orbital still moves with the same dynamics whether or not the orbital is filled with an electron. Okay? Good? So the thing that's funny about the Drude equation in these semiconductors is that if you're up at the top of the band, you have a choice of two things that both seem a little bit weird. One possibility is that you have to think about a negative mass for the electrons if you're thinking about electrons in the state. The other possibility is you think about positive mass holes, but now these are positively charged particles. Now this resolves one of our old puzzles. Old puzzle from the second day or the third day of term. Old puzzle, which was y is sine of Hall coefficient. Hall coefficient sometimes positive. So you'll recall that we derived in Drude theory that the Hall coefficient is 1 over n times the charge on the particle moving around. This is the charge on the electron. So if you have a band which is mostly empty and there are just a couple of electrons moving around, then you have Drude theory for these electrons moving around, just like we thought about in Sommerfeld theory or in Drude theory at the beginning of the term, and you'll get a Hall coefficient which is negative. But if you have a band which is mostly filled and you just have a couple of holes in the top of the band running around, then either way you look at it, whether you think about it as holes running around with a positive charge, or you think about it as electrons running around, but now the mass of the electron is negative, what you'll get is you'll get the opposite sign, because now the things carrying the charge have the wrong sign. They have positive sign instead of negative sign. So this is what Drude might have deduced way back in 1901, that it appeared that for some materials, for some reason, the charge carrier had the wrong sign. And indeed, that's what's going on. In some materials, the charge is carried by holes rather than electrons. So if you have a semiconductor and you dope it with electrons, you always get this sign of the Hall coefficient. If you dope it with holes, you'll get the opposite sign of the Hall coefficient. Now for metals, real metals like calcium or beryllium or manganese or something like that, which are not just lightly doped, where we have some complicated band structure, it's less clear what the sign of this is supposed to come out as, because you can have a situation like we discussed with calcium in the last lecture, where you have a partially filled lowest band and a partially filled highest band. So you can think of it as having some holes in the first boron zone, some holes in the first band, but some electrons in the second band. So the holes are trying to give you a positive Hall coefficient. The electrons in the second band are trying to give you a negative Hall coefficient. The two of them compete with each other, and then you have to start worrying about which one has a greater scattering time. Okay? So it gets a little bit more complicated for genuine real metals like beryllium or manganese or calcium. But in the case of a doped semiconductor, it comes out very clearly. If you have basically electron transport, you get this sign of the Hall coefficient. If you have basically hole transport, you have the opposite sign of the Hall coefficient. So far, so good? So we've resolved this one puzzle. There was something else that I mentioned when we talked about Drude theory all the way back at the beginning of the term. Remember that Drude theory works well for semiconductors. Why is that? Besides the fact that it can get the sign intelligently, the reason why Drude theory works particularly well for semiconductors is because usually when you're talking about semiconductors, you're talking about a very low density of charge carriers. You're talking about just a few electrons in the conduction band or just a few holes in the valence band because density is low. Whether we're talking about electrons in the conduction band or holes in the valence band, the density is fairly low. Well, why does that help you? The reason that Drude theory failed back when we were studying it for the first time is because we neglected Fermi statistics. We neglected the fact that the electrons were fermions, and that made us mess up all of these things like the heat capacity. We got that completely wrong because we neglected Fermi statistics. But if the density is really low, you're actually entitled to neglect Fermi statistics. Why is that? Well, if the probability of having two electrons ever sit in the same orbital is extremely low, because the density of these electrons is very low, then you can just treat these as classical particles, Maxwell-Boltzmann particles, because it's very unlikely they're going to sit in the same orbital in the first place. A sort of better defined way of saying that is the Fermi energy, given this density. The Fermi energy increases with density. If the density is low, the Fermi energy is low. If the Fermi energy is much less than the temperature, which would be true if the density is low, then you don't have to worry about Fermi statistics. You can treat the particles as being classical. So particles are classical. And you can consider just regular classical Drude theory, classical Boltzmann dynamics, Maxwell-Boltzmann distributions without worrying about Fermi distributions. So this is, yes?
Sorry, we were just wondering, do holes obey Fermi statistics then?
Do holes, yes, holes, we'll come to that in a moment, but holes also do obey Fermi statistics. You can only put, if you think about it for a second, you can only put one hole in a particular K state. If you start with the valence band filled, you can take it out once, but you can't take it out again. Okay? Yes, holes do obey Fermi statistics. They are fermions. All right. So this is actually bringing us to the realm of statistical mechanics or thermodynamics of our particles in semiconductors. So we have to start thinking about things like how many electrons get excited from the valence band to the conduction band, how did they get there, what are they doing once they're there, what's the effect of temperature. So one thing that I told you in the last lecture that I should be a little bit more honest about, we're going to go back to think about doping for a second and how doping is affected by temperature. Doping and temperature. Okay? So let's recall that when we took a N-dopant like phosphorus, phos in silicon, an N-dopant, we wrote that phosphorus equals a silicon plus one proton plus one electron. And I told you the electron goes into the conduction band, and I told you to ignore the fact that there's an extra proton. Ignore. Now, this issue of being able to ignore the extra proton that we put in addition, that is something that is actually we have to be a little bit more careful about. And we have to worry about temperature and things like that to ask whether it's OK to ignore it. So think about this a little bit more carefully. We put in a proton and we put in an electron. So what does an electron and a proton do when you put them together? What's really going to happen is you're going to form a hydrogen atom or hydrogenic atom. Hydrogenic atom. We put the electron in the conduction band, but we also put a positive charge behind. And the electron is going to bind to that positive charge. It's attracted to that positive charge by Coulomb interactions, and you form a hydrogen atom. But it's not a regular hydrogen atom. It's slightly different from a hydrogen atom because, one, m star, not m, not the mass of the electron. It's the effective mass of the electron, not the mass of the electron. The dynamics of the electron running around in the conduction band is given by m star, not the bare mass of the electron. So that's difference one. The second difference is something you learned in E&M. The Coulomb interaction, the attraction back to the proton, is e squared over 4 pi epsilon naught epsilon relative times r. R. Epsilon, a relative dielectric constant. Relative dielectric constant, not the usual e squared over 4 pi epsilon naught r. Okay? So the Coulomb interaction is reduced by the relative dielectric constant because you're living in a semiconductor, not living in the vacuum of outer space. So if you recall, we're a regular hydrogen atom, regular hydrogen atom. There's a binding energy, E binding, which is, well, okay, you probably, well, maybe you do remember this formula. It's 8 epsilon naught squared, Planck's constant squared, but you probably remember the magic number 13.6 eV, which is a Rydberg. So this is the binding energy of a regular hydrogen atom, but in a semiconductor, the binding energy, E binding, of the electron back to the proton, the additional charge that I put in with the dopant, is now m star electron e to the 4th over 8 epsilon relative epsilon naught squared over h squared, which I can then write as m star of the electron divided by the mass of the electron times 1 over epsilon relative squared times 13.6 eV. Now, this expression can be a whole lot different from 13.6 eV, and generically it's going to be a lot smaller. Typically, effective masses of electrons in semiconductors can be 1/3 of the mass of an electron. It can be even 1/10 of the mass of an electron, or even smaller. The dielectric constant in semiconductors can be numbers like 10. So that means that this number, the actual binding energy of the electron to the proton in the semiconductor, can be as much as a factor of 1,000 less than this. For example, in silicon, E binding of the electron back to its dopant nucleus is 0.044 electron volts, a much, much, much smaller number. Now, why is that important? Okay. Oh, look at this. I need that. Okay, let me put this in here. I'm going to draw the, so here's the bottom of the conduction band. Here's the top of a valence band. So when you put a dopant in, when you put the phosphorus dopant in, you form a bound state, which is a very small distance, E binding, below the bottom of the conduction band. So you gain a tiny bit of energy by binding. Instead of just sitting with k equals 0 in the conduction band, you gain a little bit of energy by binding to the positive nucleus that you came from. However, this energy here is very, very small, and at room temperature, I'll write this down, at T room, the electron breaks free. Breaks free and goes off into the conduction band. Breaks free and goes into conduction band. It's just thermally excited into the conduction band. And this is why it's okay to think about when we add phosphorus dopant to silicon, we really should just think at room temperature or a higher temperature, we should think about this as just directly adding electrons into the conduction band. If you cool it down, if you cool this, maybe I'll write that down. So doping adds electrons, adds E directly to conduction band. Or similarly, if you did the same thing with holes, when you add in the hole, it would form a bound state to the negative charge on the nucleus that we left behind. We were putting in a boron or an aluminum or something. And at finite temperature, that hole breaks free of its nucleus and runs off into the valence band. However, at low temperature, the electron becomes bound again, bound to the dopant nucleus, nucleus again. So if you were measuring the density of electrons in the conduction band, if you cooled the system down a lot, all of a sudden you would discover that the density of electrons in the conduction band was dropping because all of these electrons were getting frozen back onto the nucleus that they came from. This is known as carrier freeze-out. Carrier freeze-out. Okay. All right. So far so good? Everyone happy with this? All right. So now it's time to do some serious statistical mechanics, thinking about how many electrons we should have in the conduction band and how many holes we should have in the valence band. This is a rather important calculation that actually shows up on exams very frequently. So it's a good thing to go through several times. All right. So let's start with this sort of generic picture of the bottom of a conduction band, the top of a valence band. They don't have to have the same curvature in general. They could have different effective masses. I've drawn the effective masses being slightly different. They don't have to be aligned. It could be an indirect gap. The top of the valence band could be in a different place than the bottom of the conduction band. We'll call this energy E-conduction, EC for E-conduction. We'll call this energy EV for E-valence. This energy E-gap, E sub G. And E-gap equals E-conduction minus E-valence. And we'll imagine that the chemical potential is somewhere in the middle of the band, and we'll try to figure out where it is. All right. And so we start with the valence band being completely filled, and we're going to try to figure out what happens when we add temperature. So a couple things we're going to need. One is what the spectra are. So for energy greater than energy conduction, we have energy as a function of K is energy conduction plus h bar squared K minus K min squared over 2 m star electron. And then for energy less than E valence, we have the upside down parabola Ek equals E valence minus h bar squared K minus K max squared over 2 m star whole. And m star whole, remember, is positive. So we have a negative curvature of the top of the band. And then we have to think about counting states. So counting states. And we'll think back to when we did Sommerfeld theory for free electrons. For free electrons, we had, well, our energy was E equals h bar squared K squared over 2m. And the density of states, so the density of states per unit volume, well, G of E was given by this expression, which we calculated, 2 mass to 3 halves over 2 pi squared h bar cubed epsilon to the 1/2. We calculated this, I think, on the second or third day of the term. This is the density of states per unit volume. states per volume. So we'd like to use exactly the same calculation except for the conduction band and the valence band here. So without actually doing the work, it's pretty easy to see what the result is going to come out as. The density of states in the conduction band for E greater than E conduction is going to be 2 mass of the electron star to the 3/2 divided by the same 2 pi squared h bar cubed. And there's the same E to the 1/2, but it's E minus E conduction band. So you're measuring the energy with respect to the bottom of the conduction band. The parabola starts at the bottom of the conduction band. But otherwise, it's exactly the same calculation. People happy with that? OK, good. So G valence, maybe a little bit more complicated, but not too much more complicated, is 2 m star whole 3/2 over 2 pi squared h bar cubed. And here we measure E valence minus E to the 1/2. And we're measuring going in the downward direction. Well, we need this thing to the 1/2 to be a positive number, so it has to be E valence minus E. We measure going down. We get an increasing number of states as we go down to lower energy. Good? All right. So then we can write in conduction band. We just use our statistical mechanics. The density of electrons, density n of electrons, of E's, is given by n as a function of t, that's an n, equals the integral from the bottom of the conduction band up to energy infinity, d energy, density of states as a function of energy, and the Fermi factor, beta energy minus mu. Okay, so the integral of the density of states is basically a sum over all eigenstates, and the Fermi factor is the probability that that eigenstate is going to be filled. So this is just counting up all the states that are filled at a given temperature, but we need to know what the chemical potential is. Okay? So now we're going to, well, let's write out the Fermi function here. The Fermi function is 1 over e to the beta energy minus mu plus 1. Now if we're at fairly high temperature, or if the density is low, or strictly speaking, what we need is beta energy minus mu is much greater than 1. This means that mu is much below EC, meaning that below by at least the amount of the temperature. So fairly well below the bottom of the conduction band. And that's pretty easy because the gaps between the conduction band and the valence band can be a couple of electron volts, much bigger than typical temperatures. That means that NF can be approximated by, well, you can just drop the plus 1, and you get just the regular Boltzmann factor. This is just Boltzmann, Maxwell-Boltzmann. Maxwell-Boltzmann. So let's put that in, and we have n of t then is going to be integral d energy EC from the bottom of the conduction band up to infinity of g of energy and then the Maxwell-Boltzmann factor e to the minus beta energy minus mu, making that approximation. And this is temperature. Then how do we do this integral? Well, first thing we're going to do is we're going to well, what are we going to do? We're going to write out what this G is. So this has a 2 m star of the electron to the 3/2, and it has a 2 pi squared h bar cubed, and then it's integral d energy of the conduction band to infinity times E minus E conduction to the 1/2, and then e to the minus beta energy minus mu. So this is the e to the 1/2 that we have up there. And we have to do this integral. And the way we do this integral is by shifting out a factor of e to the minus beta EC minus mu out front. So then we're left with an integral d energy from EC to infinity, E minus EC to the 1/2, and then e to the minus beta E minus EC. which is nice. We can then write, if we want, well, x equals e minus ec if we want. So this becomes integral of dx from 0 to infinity, x to the 1/2, e to the minus beta x. Then we can do that integral by defining y squared equals x. This becomes a simple Gaussian integral, and we get beta to the minus 3/2 times square root of pi over 2. Okay? So we put that all together, and we end up getting the density of electrons in the conduction band as a function of t is then putting together all those factors, 1/4 2 mass of the electron star kBt over pi h bar squared to the 3/2 e to the minus beta energy of the conduction band minus mu. So this is our expression. We now know how many electrons there are in the conduction band as a function of temperature and as a function of mu. The important thing to take away, there's some prefactors here which aren't that crucial. The important thing here to take away is that it's basically activated. That you have to activate the energy up from the chemical potential into the conduction band in order to get an electron into the conduction band. As you drop the temperature, the number of electrons in the conduction band is going to drop exponentially. Okay? All right. So far, so good. Now we have to do the same thing for holes. I think we can still do this in time. So the number of holes in the valence band, well, okay, let's write that. That's going to be integral from minus infinity to the top of the valence band, d energy, the density of states in the valence band, and then I'll write 1 minus the Fermi factor in the valence band, beta epsilon minus mu. Why is that? Well, if the probability of an electron being a state is the Fermi function, then the probability of a hole being the state, the absence of an electron, is 1 minus the Fermi function. Good? All right? So this factor here, we're going to basically go through the same manipulation. So this is, we can write this as 1 minus 1 over e to the beta epsilon minus mu plus 1. That becomes, oh, I'm running out of space, aren't I? All right. Well, this thing becomes, this whole thing here becomes 1 over 1 plus e to the minus beta e minus mu. That maybe took 2 steps, but you can check algebraically that's true. And again, we're going to assume something analogous to what, do I have more space somewhere? No? All right, maybe I don't. So we're going to assume something analogous to what we assumed for the electrons. We'll assume that the chemical potential is not too close. Too close meaning within the temperature, within a range of kBt of the top of the valence band, EV, in which case this thing can be approximated as, this whole thing here can be approximately equal to the Boltzmann factor, e to the beta epsilon minus mu, much less than 1. Okay? So it's again more or less the same story, but here you have to realize that energy is less than mu, and you're activating a hole downwards into the valence band rather than an electron up into the conduction band. So plugging in the expression for the density of states in the valence band, we get 2 m star whole to the 3/2 2 pi squared h bar cubed integral d energy minus infinity to e valence minus e to the 1/2 e to the beta epsilon minus mu. And exactly the same manipulations with maybe a couple minus signs put in various places. I think you're supposed to do it for homework, so maybe I won't go through it. And also, I'm running out of time. So this whole thing becomes, at the end of the day, a very analogous expression to what we found above, is 1/4 2 m star whole kBt over pi h bar squared, all to the 3/2 e to the minus beta mu minus e valence. And again, it's the same story. You have some prefactors here but the important part is that you have to activate a hole down from the chemical potential into the valence band, because it takes energy to push a hole down into the valence band. The holes want to go up as much as possible. So if we knew the chemical potential and we knew the temperature, we could figure out the density of electrons in the conduction band and the density of holes in the valence band. But now there's a trick, and the trick is to look at the product of n of t times p of t. Let's do that. We get a bunch of factors. So 1/2 out front, kBt over pi h bar squared cubed. Then there's a mass of an electron, star, mass of hole, star to the 3/2. And then if you look at the exponential factors, you'll notice that the exponential factors, e to the minus beta mu's and the e to the plus beta mu, will cancel. So the only thing that's left over is e to the minus beta, E conduction minus E valence. E conduction minus E valence is E gap. So if you know the gap energy and you know the temperature, you know the product of the number of electrons in the conduction band and the number of holes in the valence band. And this law, very important law, is known as the law of mass action. Law of mass action. If you talk to chemists, they know this. They have a law of mass action, and the nomenclature comes from this, from chemistry. Actually, I won't maybe go through why it is it's called the same thing as the law of mass action in chemistry. But the important thing here to realize is that the product is independent of the chemical potential, and that means it's independent of how we've doped the system. So let's just a couple more things. If we have an intrinsic, oh, did I use that word? I never used that word before. So intrinsic means undoped. So if I have an intrinsic semiconductor, I should have probably used that word in the last lecture. For an intrinsic semiconductor, the density of electrons in the conduction band equals the density of holes in the valence band, because each time you take an electron out of the valence band and you put it up in the conduction band, you created one hole and you created one electron. In which case, you can just take the square root of the law of mass action and you can tell what N and P are at any temperature. So you're good there. But for a doped system, then it's more complicated. Then we add dopants, and we have the number of electrons in the conduction band minus the number of holes in the valence band equals the number of donor impurities minus the number of acceptor impurities. Because basically, each time you add a donor impurity, you add one electron into the conduction band without adding a hole into the valence band. And each time you add an acceptor, you add a hole into the valence band without adding an electron into the conduction band. And this is true as long as T is greater than T freeze out, where the electrons in the conduction band get bound to their donors, and the holes in the valence band get bound to their acceptors. So the key thing to realize here is that the product of N and P is fixed, independent of the doping. The difference of N and P depends on the doping. This means that as you add as you add donor impurities, the chemical potential goes up. So you get more electrons and fewer holes, but the product of the number of electrons and the number of holes stays fixed. As you add more acceptors, the chemical potential goes down. You get more holes than electrons, but the product of the two stays fixed. Maybe I'll even write that before calling it quits. Adding donors, mu goes up. Mu goes up. We're adding acceptors. Mu goes down. But because of the law of mass action, the product of those two is always going to stay fixed. All right, so next time we'll pick up and actually talk about some real semiconductor devices and the devices that change the world, like the transistor. And I'll see you, I think, Wednesday. Is it Wednesday? I think it's Wednesday. Okay, have a good weekend.